Welcome to the fourth part of our search for extraterrestrial life. In the previous videos, we focused on physical, biochemical, and astronomical issues, in particular, all the preconditions that must be fulfilled for the emergence of life. Now we want to take a big leap and look not only for life, but for intelligent life, and for technologically advanced civilizations in space. Nevertheless, we still do not know whether life is an exceptional phenomenon, or whether it must inevitably arise wherever the conditions are suitable for it. Common sense leads us to assume that there are many planets where microbic life has evolved. It can likewise be concluded that the probability of more complex life forms, such as plants and animals, is not that high. As a logical consequence, we further conclude that the emergence of what we call intelligent life, however intelligence is defined, is even more unlikely. And if we go one step further and assume advanced civilizations in space, which are perhaps on a similar or even higher level of development than we have, these would probably have to be the most unlikely and rarest of all forms of life. Nevertheless, the universe, with its unimaginably large number of galaxies, stars, and planets, is large enough to make even the seemingly most improbable assumption probable, and the rarest in common. Even if there was only one civilization in every galaxy, there would be billions of them throughout the universe. However, any kind of exchange with them over intergalactic distances of millions of light years would be impossible. It may be useful to know that we are only one of many life forms in space, but it is much more important for us to know whether we are the only intelligent species. Philosophical, social, and perhaps even technological implications would be much deeper. A possible dialogue with other intelligent civilizations in our galaxy would have an impact on every aspect of our existence. In fact, this would be by far the most significant discovery in human history. On the other hand, if other civilizations do not exist, we would be forced to explore the purpose of our existence in a universe in which we are unique. At the end of this video, we will take a look at the Drake equation, which aims to give an estimate of how many intelligent extraterrestrial civilizations exist in the galaxy, based on a range of known and unknown variables. Research on exoplanets suggests that there could be millions of Earth-like planets alone in our galaxy, so the odds may not be that bad. In roughly 3.5 billion years, life on Earth has gone through 4 different stages of evolution, from the simplest organic building blocks to us humans. First, there was physical evolution, which concluded with the formation of Earth and the fulfillment of all the prerequisites necessary for the emergence and development of life. Then, chemical and biochemical evolution set in, to turn the building blocks of life into what we call life. The subsequent biological evolution, which took the longest time, required billions of years to evolve simple cells into complex living beings, always influenced by mass extinctions and other unpredictable impacts. Finally, at least one of many billions of very different species that have ever existed on Earth entered a 4th stage of evolution, which distinguishes this life form from all others. Namely, the cultural and technological evolution. It all started with the development of what we call intelligence. But what is intelligence? The word comes from Latin, intellego, meaning to recognize, understand, or comprehend. In very general terms, intelligence is the ability to learn from experience. More specifically, the mental and cognitive abilities of a living being, whether human, animal, or alien, that lead to the solution of problems or adaptation to its environment. In addition, complex emotions are very closely linked to intelligence, or in other words, emotions presuppose intelligence. Researchers from a wide variety of disciplines, such as medicine, anthropology, biology, psychology, and philosophy, however, are by no means in agreement on how and whether intelligence can be defined in an all-encompassing way. So, it is quite similar with the concept of intelligence as with the concept of life itself. We will see that this also applies to the concepts of society and civilization, although there are many very different manifestations on our planet, and even more varieties and species of life. A similar question arises as to whether intelligence is a purely human trait. In fact, intelligent behavior and emotions can be observed in many animals as well. The same is true for consciousness and self-awareness. And even in biochemistry, there seem to be processes which could be considered intelligent. Thus, life itself seems to be capable of learning, by having some sort of a problem-solving department, and that is no less than evolution. For billions of years, evolution has repeatedly gone in directions that could be interpreted as the result of decisions, or as being based on experience. These experiences are stored inside the DNA and carried out by biological processes, such as genetic modification, adaptation, selection, and mutation, and with the aim of maintaining the continuity and improving the procedures of life. So, is evolution intelligent? Or are we just mixing it up? Some authors therefore argue the very controversial thesis that the whole of nature, and thus possibly our entire planet, is an intelligent organism. This is the so-called Gaia hypothesis. However, the seeming knowledge gathered by evolution is not comparable with the brain-controlled intelligence of living beings. This is already reflected in the speed with which genetic processes take place. Evolution thinks and acts much slower, and converts genetic modifications into biological function only generations later. So, mind, intellect, which takes place in our brains, and leads living beings to decisions and conscious actions in fractions of a second, is therefore obviously something quite different. In philosophy, intelligence is often associated with the human ability to think. Historically, it contrasts with instinct, which is more like reflex than deliberate thinking. The seemingly intelligence of many animals is therefore often interpreted as extended instinctual behavior, rather than true intelligence. However, many species have tremendous intellectual capacity, which is manifested in a variety of ways. Some of them, such as primates, elephants, whales, and corvids, are able to recognize their mirror image. Human children do not acquire this ability until they are in their second year of life. Evidence for animal intelligence can be seen, for example, in their ability to manufacture and use tools. These abilities are not unique to primates, many of whom use tools, as a matter of course, to reach food. Likewise, it is evident in the complex language of some species, such as cetaceans. Male humpback whales communicate through coherent songs that last up to several hours. These songs are among the most complex forms of communication in wildlife. Intelligent behavior is also identifiable in the fact that many animals tend to form organized social structures, but also in their relationship with death, which is particularly striking with elephants. Some authors even discuss the intelligence of plants, as trees may be able to communicate with each other, using their root network. However, since plants have neither a brain nor a nervous system, a comparison with the intelligence of humans and animals is probably off limits. Because all major human abilities, what we perceive and feel, what we know and think, or how we behave, are controlled by a giant network of nerve cells, which we call brain. It regulates all organs and physical functions. A distinction is made between different areas in the brain, with each area being specialized for certain tasks. Ultimately, however, all these areas work together. Although neuroscientists have been trying to figure out how our brains work for decades, we still have a long way to go to fully understand it. Some compare it to a powerful biological computer, capable not only of storing and processing knowledge, but also of controlling reactions and behavior. This takes place by means of nerve cells, the neurons. Due to their extensions, called axons and dendrites, the neurons, and so the different areas of the brain, can connect and communicate with each other. They exchange information at specific links, the synapses. There are countless of them in our brain. Repeated exchange of information between neurons allows synapses to form and strengthen. This speeds up and simplifies the information transfer. Every time we learn something or have a new experience, a new connection is formed. We actually have quite large brains in relation to most animals, as well as to our own body size. This detail seems to play an important role in development of intelligence, But it is not the only matter. Another crucial factor is how interconnected the individual neurons and brain areas are. The main connections in our brains are formed even before birth. However, brain research has shown that neural links build up throughout life. While old connections may change or strengthen, new ones are constantly being formed. This happens especially when neurons are used intensively, for example through learning and experience. Actually, learning is not a purely human ability. Juvenile animals are also able to learn by imitating the behavior of adults. Learning processes always involve the formation and strengthening of neural connections. This is no different for animals than it is for humans. Compared to the brains of animals, the long time of development of the human brain is the decisive factor for the progress of intelligence. Most animals are already born with nearly fully developed brains. Consequently, many species are able to walk and recognize dangers shortly after birth. They stand on their own legs within minutes and run after their mothers, since every second of immobility makes them easy prey. So, animals come into life almost fully developed. However, this doesn't work for humans. If we take chimpanzees as an example, a human pregnancy would have to take almost twice as long, about 16 months, for both chimpanzees and humans to show similar abilities at birth. Instead, human babies are born before their brains are fully developed, which actually makes every human baby a premature birth. This is mainly for physical reasons, since otherwise birth would not be possible, due to the size of the human skull. Already at birth, a human baby's brain is about the size of an adult chimpanzee brain. On the other hand, at some point during pregnancy, the chimpanzee brain stops growing, and the rate of growth even decreases before birth. However, the human brain continues to grow, and so does the circumference of the baby's skull. Therefore, nature has provided a compromise. The human female anatomy is adapted to deliver a baby after a maximum of 9 months of pregnancy. In turn, the baby's brain is still not fully developed at birth, but continues to grow postpartum. As a result, unlike many animal species, human babies are completely helpless right after birth. They do not even acquire the ability of walking until they are about 1 year old. With our early ancestors, prehistoric humans, it was probably different. For several thousand years, we have been at the top of the food chain, or at least quite high up. Therefore, human babies have not had to flee from predators, or search for food on their own, right after birth. However, our baby's helplessness requires very caring parents. It is therefore no coincidence that parental care is particularly evident in higher species, for example intelligent mammals, whereas it is completely unknown in other species such as reptiles and insects. An essential process, which sets us apart from most animals, and presumably leads to intelligence, takes place in the years after birth. Side by side with an equally slow physical growth, our brains also develop slowly and over many years. Already during the first years, the human brain grows by 3 times its volume. Brain development is not complete in young people until they are in their early to mid-20s. And during this time, an unimaginable number of neural connections are formed. In order to understand how cultural evolution was able to develop in such a progressive way, we must consider biological evolution in parallel. For evolution to take place, genetic changes are indispensable. This also applies to cultural evolution. Technological developments were only possible through specific biological characteristics. Due to cultural evolution, humans also had better reproductive success and were thus able to spread more quickly. One of the most significant changes was a substantial increase in human brain volume, which took place simultaneously with the so-called Neolithic Revolution, about 10,000 years ago. People used intellectual abilities mainly to cope with everyday life. It was simply a matter of survival for the individual. However, since humans have always been social beings, it was also about the survival of the community. With the origin of modern humans, living beings had emerged that were aware of their own existence. At that time, the transition from hunter and nomadic life to sedentary agriculture began. People began to grow crops and breed animals. Technological improvements were also driven by the shift to agriculture. With the emergence of language, knowledge could be passed down through generations. Around 5,000 years ago, humans began to develop the first writings. This enabled an entirely new way of communication and for storage of knowledge and information. Until then, people only used individual symbols and pictures, such as cave paintings. The enlarged human brain was a turning point in history. Only a larger and more efficient brain made differentiated language and more complex cerebral processes possible. As a result, people were able to communicate better with each other and share knowledge more efficiently. This, in turn, drove cultural and technological development. Another important ability of intelligent living beings is that of communication. There are many ways of communication in nature, for example in animals. Communication always involves the exchange or transmission of information, which can take place in various ways, for example non-verbally, through sounds, gestures, and behavior. In the course of cultural evolution, humans have learned to communicate both verbally and in writing. In any communication, there is always a sender and a receiver. A distinction is made between one-way, two-way, and multi-way communication. One-way communication takes place when a receiver only gets a message from a sender, without sending a message by himself. An exchange of information for mutual benefit, however, is only achieved with two-way communication, for example, in conversation. We will yet realize that two-way communication with extraterrestrials, which are dozens or hundreds of light years away, is simply impossible. Of course, this is due to the vast distances in space and the limited speed of light. Thus, even electromagnetic signals, with which we mainly communicate over long distances, such as light or radio signals, have to travel dozens or hundreds of years between sender and receiver. It should be clear to everyone that no reasonable conversation is possible in this way. So, for meaningful communication to be at least rudimentarily possible, any two civilizations must not be too far apart, and even then, all involved must deal with several years to pass between question and answer. Furthermore, both civilizations communicating with each other should have a similar level of technological evolution. Otherwise, all communication attempts would be doomed to failure. Since with us humans, technology was inseparably connected with cultural evolution from the beginning, we might also assume a similar level of development in cultural history. This graphical timeline is a simplified representation of our human history. The colored areas mark different historical epochs, beginning with the Neolithic and up to an unknown future. The green area is our present, the age of communication by means of radio technology, which began with the Industrial Revolution in the mid-19th century. In this thought experiment, we want to assume that radio technology will not play a role as a communication technology into distant future, and that future generations may find more efficient technologies for interstellar communication. For most of human history, our technical progress has been quite slow. For millennia, we moved only by horse and carriage, fought with cut and thrust weapons, made light and cooked our food with open fires. It was only since the Industrial Revolution that technology has taken a quantum leap. Gas, electricity, telegraphy, all of this has only been available to us for less than 1.5 centuries. Therefore, we have only been able to communicate by means of radio technology, that is, by sending and receiving radio signals and any messages within, for about 120 years. And it is only since this time that we have been sending radio signals into space, even if unconsciously. These radio signals, which were transmitted by the first wireless telegraphs, have unintentionally spread into space as well. Radio waves travel at the speed of light, so these signals consequently reached a radius of about 120 light-years around our solar system. Within this 120 light-year radius, there are more than 20,000 stars, most of them red dwarfs, but they may well have life-friendly planets. so our civilization might have been noticed. But for even more distant civilizations, beyond this 120 light-year radius, our Earth would be a silent and thus apparently uninhabited world. On the other hand, we could be surrounded by numerous civilizations unable to communicate with us, as they might be at a more primitive, or possibly on an even more advanced stage of evolution. A civilization younger than ours could be at the evolutionary level of our Middle Ages, as in this example. Even if we would eavesdrop on their planet, we wouldn't pick up anything. And by the time this civilization invents radio communication, some centuries later, we may already have advanced in such a way that we no longer use this technology. Or we might not exist anymore. The same would apply to aliens technically hundreds or thousands of years ahead of us. They may have sent radio signals centuries ago, or tried to pick up signals from Earth, back when we were still in the Middle Ages. Thus, they were unsuccessful in every communication attempt as well. And maybe, today they no longer do, or perhaps they have ceased to exist. So, there are two major problems for any interstellar civilizations to communicate with each other, by radio or any other electromagnetic waves. First, they must not be too far apart. If they are 120 light-years away, the radio signals will be 120 years on the way too. The limited speed of light reduces any attempt to one-way communication to a single hello. And that's it for several human lifetimes. And secondly, they both must use the same or comparable technology. This presupposes a similar technological development, and thus possibly also a similar cultural or historical level of evolution. In other words, two civilizations must be approximately synchronous in level of development. However, the probability for this is clearly lower than that of finding many civilizations on very different levels. Nevertheless, even a simple hello, if we could identify it clearly and without doubt as extraterrestrial origin, probably would be better than nothing at first. It would at least give us the certainty that there is somebody out there. Or at least there once was someone. Actually, we had to start even earlier and first define what civilization means at all, and whether our definitions are applicable to extraterrestrials. Most of our definitions of civilization rather describe the common features of various societies on Earth, whether past or present, and by no means the characteristics of hypothetical extraterrestrial civilizations. Just as with the concepts of life and intelligence, we are again forced to adopt an anthropomorphic point of view, that is, a view based on the human example. However, this cannot be avoided, since we do not know any other societies or civilizations than those on our planet. Nevertheless, it is also not completely unjustified, since at least a minimum similarity is necessary, if a possible contact with extraterrestrials should be of interest for us. But what signals should we look for? With our own civilization, we realize that we have left quite few traces in our vicinity, apart from space probes that have reached the edge of the solar system. The situation is different with radio signals, which we have been sending into space more or less intentionally for about a century. Alien observers, having an adequate receiver technology, and being not more than about 120 light-years away, should definitely have noticed our planet, especially in the range of centimeter and millimeter radio waves. So they would pick up our technology signature, as this is called by analogy with biosignatures. Can we conclude that the easiest to discover life form is an extraterrestrial civilization, which is sending out radio signals? In fact, an important field of SETI research is based on this, relying on the existence of civilizations sending out signals into space. However, we face many problems here, conceptual as well as practical. First, our physical theories are limited. Perhaps radio waves, which have been the main focus of SETI research for decades, are not the best means of communication. Possibly extraterrestrial civilizations use much more efficient methods that we do not yet know. For some time, other communication possibilities have been discussed, such as powerful lasers, or even communication at the quantum information processing level. Today, scientists are researching quantum communications, and in the future, astronomers may search for quantum transmissions from extraterrestrial civilizations. But even if they use radio technology, many unknown factors remain. For example, about signal frequency, bandwidth, wavelength modulation, or receiver orientation, and so on. Even if one day we succeeded in receiving a message, which could be identified without any doubt as an extraterrestrial communication attempt, there would still be the problem of deciphering it. What might the grammar and semantics of an alien language look like? Both the specific search for signals and the considerations about extraterrestrial civilizations and their implications once more force us to establish relationships between terms for which we know only one example, and that is our own. Nevertheless, there could be several ways to detect alien civilizations. By trying to pick up signals from an alien source, or by sending out signals ourselves, and then hoping they will be picked up and answered. And finally, we could send out space probes, carrying messages or information, and maybe, one day, our probes will be fast enough to reach distant planetary systems within the span of a human lifetime. A direct message addressed to extraterrestrial civilizations has been sent from Earth into space only once so far. In 1974, a coded transmission was emitted by the Arecibo radio telescope in Puerto Rico, in the direction of the globular star cluster M13, 25,000 light-years away. Of course, the huge distance of the chosen target makes it very unlikely to get a reply within the next 50,000 years. Nevertheless, the idea behind this choice was that due to the enormous stellar density inside the cluster, which consists of at least 300,000 stars, a higher probability was expected for the signal to reach as many planets as possible. The message, which was transmitted only once, on November 16, 1974, consisted of 1,679 bits of information, binary coded and arranged in a grid of 23 rows and 73 columns, both prime numbers, to form a simple image. At the beginning, the message contained the numbers from 1 to 10, in order to immediately provide the receiver with a key for decoding, followed by binary codes representing the 5 most important elements of biochemistry: hydrogen, carbon, nitrogen, oxygen, and phosphorus, as well as the description and structure of the 4 nucleotides, the building blocks of DNA. The message also addresses information about human anatomy and mankind, giving, for example, the population number living on Earth at the time of the message, which was 4.3 billion. Our solar system and the sending telescope are described at the end of the transmission. The Arecibo message was more of a symbolic act than a true attempt at communication, as the entire transmission lasted only 3 minutes. Therefore, this action is viewed with great skepticism today. In order to increase the probability that this message will be received at all and identified as an artificial origin, it should have been repeated more frequently, at best over several days. This was not done since the energy required to actively transmit signals into space is enormous, and the benefits are questionable. Furthermore, there may be good reasons why civilizations do not want to communicate even though they are capable of doing so, or even actively disguise their planet's technological signatures. We also have repeatedly sent space probes with messages intended for extraterrestrials, although in all cases it was not the main task of their missions. Instead, some space probes, that would eventually complete their primary mission of exploring planets in the outer solar system and then be sent on into the depths of interstellar space, were additionally equipped with information panels and other media. The best known are the Pioneer plates and the Voyager records, which are intended to carry binary-coded messages to extraterrestrials, in addition to audio messages. Ultimately, such cosmic bottle messages should be regarded as symbolic acts as well. The probability that one of them will ever be found by intelligent aliens, who will then also be able to decode the messages, is orders of magnitude less than the probability that the Arecibo message will one day be received by another civilization. Although there are speculations that an alien probe has already flown through our solar system. In 2017, astronomers discovered a celestial body about 200 meters long. Coming from deep space, that object was speeding up as it made its way through our solar system, yet it had no identifiable propulsion. Even scientists speculated whether it could be an artificial object, such as an extraterrestrial space probe. However, as usual, no one has been able to provide clear proof of this, especially since no emission or any communication attempts were detected from this object, even if some YouTube videos claim otherwise. To most researchers, that object, who was called Oumuamua, was just one of many comet nuclei, as there are countless others traveling among the stars. The best strategy for SETI is to use the most economical and efficient method. Intercepting signals sent out by an extraterrestrial civilization seems to be the simplest and least expensive method. These signals could be sent out for several reasons. Similar to our first radio transmissions, they may have been emitted into space unconsciously or unintentionally, perhaps as a byproduct of their everyday activity or communication with their outposts. However, such radio emission would not be particularly intense and probably impossible to distinguish from natural radio background noise. Yet, alien signals could also be intentionally aimed into space to contact other civilizations. In this case, intelligent beings would certainly know that due to the vast interstellar distances, only one-way communication is possible. Therefore, they would take care that the receiver, which is us, is able to clearly identify their signals as artificial messages. For example, an artificial signal should be many times stronger than the background noise, since radio signals are always subject to scattering and attenuation by atoms in space. The risk is quite high that a long-traveled radio signal is weakened by frequent interaction to such an extent that only a weak carrier wave arrives, deprived of any message. So, an alien radio signal would have to be strong enough that a possible message intentionally added to the signal by modulation could still be extracted. Such a message may consist of a series of numbers, like the endless repetition of an irrational number, for example, pi, or square root of 2, or in the repetition of prime numbers. In the 1997 motion picture Contact, adapted from Carl Sagan's novel by the same name, astronomers pick up a repeating signal from the nearby star Vega, and quickly realize the message contains the sequence of 261 prime numbers.
Come on. All right, it's restarting. Wait a minute. Those are numbers. That was a 3. The one before it was a 2. Base 10 numbers. Just start counting now. See how far we can get. 1. 7. Those are primes. 2, 3, 5, 7. Those are all prime numbers. And there's no way that's a natural phenomenon.
Holy shit.
Okay, let's just calm down and pull up the star file on Vega.
Primes are characterized by their indeterminacy, which means that complex sequences of prime numbers are usually not generated by natural processes. Therefore, they could be used by any civilization to indicate the artificial origin of a signal. Modern SETI research began with an article published in 1959 by physicists Giuseppe Cacconi and Philip Morrison in the weekly science journal Nature. In this, the scientists concluded that microwave frequencies between 1 and 10 GHz were best suited for interstellar communications. Below 1 GHz, the so-called synchrotron radiation begins, which is caused by electrons accelerated through magnetic fields. Above 10 GHz, the radiation from hydrogen and oxygen atoms in our Earth's atmosphere interferes with any radio signals. Thus, the lower limit of this microwave window is particularly well suited for interstellar communication. Basically, it is easier sending and receiving signals with low frequencies than those with higher wavelengths. They are also more suitable because of the Doppler effect, which is caused by planetary motions. This effect causes a signal frequency change in the course of a transmission, and the higher the frequency of the transmitted signal, the more serious this change. Cacconi and Morrison concluded that in particular the 1.42 GHz frequency, which is called the H1 line or 21 cm line, and which is identical with the frequency of neutral hydrogen, could be interesting for interstellar transmission. The other limit within the radio spectrum is at the wavelength of hydroxyl, at 1.72 GHz. The space between both frequencies of hydrogen and hydroxyl is therefore called the water hole. In order to receive a radio transmission from an alien civilization, scanning the most common frequencies should be the most promising way, since it is unknown what frequency aliens might be using. Since signals should be stronger than the radiation from the stars and other natural sources, it should not be useful to send out strong signals across a wide range of wavelengths. Much more likely would be a signal transmitted on a very narrow band of frequencies. This means that a large number of narrow channels must be scanned. The first attempt to capture signals took place in 1960. Astronomer Frank Drake, who was later also largely involved in creating the Arecibo message, used the 85-foot Green Bank radio telescope to explore two neighboring sun-like stars, Epsilon Eridani and Tau Ceti. Both stars were chosen for their close similarity to the Sun, and at distances of about 11 to 12 light-years, they can be considered among the neighbors of our planetary system. Drake scanned both systems, hoping to pick up signals from extraterrestrial intelligences. However, at the end of the 150-hour observation period, magnetic tapes recorded nothing else than random noise, plus a signal of a secret military experiment. Drake had shown what the search for our cosmic neighbors might look like. One of the most prominent radio observatories where various SETI projects were carried out was the Arecibo telescope in Puerto Rico, which unfortunately collapsed a few years ago and was subsequently decommissioned. After becoming famous for the 1974 message, it has since been used many times to search for extraterrestrial signals. For example, from 1998 to 2004, as part of the Phoenix Project, which was the most extensive search program for extraterrestrial intelligence to that time. For this project, the constructive features of the radio telescope were taken into account. The Arecibo telescope had an immovable main reflector with a diameter of 305 meters, or 1,000 feet, which was embedded in a natural valley. With detection instruments movably mounted on a platform suspended above the reflector, it allowed observation of a range of nearly 20 degrees around the zenith. Radio sources thus had to pass through the telescope's field of view, due to the Earth's rotation, in order to be picked up by the detectors. When picking up individual radio signals, interfering signals of terrestrial origin must be filtered out, in addition to background noise. All received signals initially increased in intensity as the source rotated into the telescope's field of detection. After the intensity peak, the signals lost strength again. Each run took about 12 seconds. Terrestrial signals would be received either much shorter, or even permanently, and of course, usually much stronger. This diagram is a simplified representation of a random radio signal, as detected by the Arecibo radio telescope during the 12-second run. The horizontal axis represents the 12-second signal pass. The vertical axis is the signal's wavelength or frequency, respectively, its peak strength. The radio signal starts weakly on the left side and becomes stronger towards the right. After 6 seconds, it reaches maximum intensity in the middle and levels off again over the next 6 seconds. This shows a broadband signal of natural origin, such as an astronomical radio source, scattered over a quite wide range of frequencies. However, such a broadband signal is more like that of a star or another natural astronomical radio source, for example, a radio galaxy. The common assumption is that extraterrestrial civilizations would send signals in the most efficient way, and that would be mainly narrowband signals, as is necessary for the transmission of data. In addition, narrowband signals are much easier to filter out compared to the background noise. Therefore, researchers quickly realized that new receivers would have to be developed to chop the incoming radiation into millions of channels with very narrow bandwidths, and to analyze the signals in each channel immediately. This example shows a narrowband signal on a randomly selected bandwidth within a narrow frequency spectrum. It also gets stronger and weaker over the 12-second period. Like broadband signals, they are also subject to scattering and attenuation, which is why certain patterns are sought. Now, a content can be added to this signal, which initially consists only of a carrier wave, by means of modulation. For example, a regular and complex pulse pattern would indicate that the signal is artificial. Studies have been done on how sending a signal that can be easily found and decoded, and whether it could be transmitted a coding or modulation through this pattern. But in fact, there are also natural radio sources in space which send out regular radio pulses, the so-called pulsars. The first pulsar was discovered by Jocelyn Bell Burnell during her search for radio sources on November 28, 1967, at the Mullard Radio Astronomy Observatory, near Cambridge. The signals of the pulsar were characterized by unusual regularity of the emitted waves, so that at first they were thought to be artificial signals, possibly coming from an extraterrestrial civilization. The pulsar signals were therefore called little green men signals. Pulsars are rapidly spinning neutron stars, surrounded by a very strong magnetic field. As a result of their fast rotation, electromagnetic waves sweep through space like the beam of a lighthouse. Only if Earth is streaked by the radiation beam, the pulsar can be detected. However, pulsars send out electromagnetic waves over a wide range of frequencies, not only in radio, but also in visible light, or even X-rays. As we have learned, an artificial pulsed radio signal would presumably be narrowband. Furthermore, since the positions of Earth and radio source should not be constant to each other, we must calculate with an object in relative movement to Earth with a variable signal. This is the well-known Doppler effect. Likewise, a change in frequency would be possible. So, the frequency of the signal can rise or fall slightly within the 12 seconds run. These are called chirp signals. Likewise, there could be pulsed and chirp signals. All of them could most likely not be of natural origin. However, Project Phoenix, which also included the Parkes Radio Telescope in Australia and the Green Bank Radio Telescope, was terminated in 2004 after 800 stars within a search radius of 200 light-years had been examined without results. It once again became evident that such SETI projects generate very large amounts of data, whose evaluation is highly time-consuming. The solution to this problem was to involve volunteers from all around the world, willing to donate the computing time and power of their personal computers. To do this, Berkeley University in California sent small packets of data to hundreds of thousands of private computers, on which the analysis ran in the background. For SETI at Home, as the project has been named, the Arecibo Radio Telescope was even equipped with an additional receiver, which recorded radio signals while the telescope was making other scientific observations. SETI at Home thus received a large amount of radio data, without occupying any telescope time of its own. Since 1999, the home computers participating in the SETI at Home project produced a total of almost 2.3 million years of computing time. During this, approximately 1.8 billion results have been received from nearly 5.5 million users, although only about 250,000 were active at any given time, by sending results back to the servers. By now, SETI at Home has been suspended, or as the project management says, the project is in hibernation. Currently no more tasks are distributed, only the message boards and the data analysis are still operated. Even though the project has not yet provided definitive proof of extraterrestrial intelligence, it has identified some spots on the star maps that need to be analyzed in more detail. So, has anything conclusive ever been picked up at all? To this day, only a fraction of the data collected by the numerous completed and ongoing SETI projects has been analyzed. Officially, it has not been confirmed yet that any of the SETI projects has been able to identify a signal unambiguously and without any doubt as being of extraterrestrial and intelligent origin. Even if many, especially some channels here on YouTube, claim that they have long discovered such signals, but would keep them secret. This also applies to the following, probably the highlight of all alleged signals ever received: the famous WOW signal. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University recorded a narrowband radio signal at 1420 MHz, coming from the constellation of Sagittarius. It was significantly stronger than the background noise at 30 times the standard deviation. The frequency also corresponded exactly to the 21 cm wavelength of neutral hydrogen. The signal was so strong that astrophysicist Jerry Emin wrote the word "wow" on the computer printout. This was to give the signal its later name. The printout mostly shows numerical values, moving in the range of 1 to 2, which corresponds to the intensity of the radio background noise. But at this point, the intensity increases to such an extent that the scale was blown up. The intensity scale starts with the numbers 1 to 9, and when 9 was no longer sufficient, it continued through the letters A to Z, with increasing signal strength. At its peak, the wow signal, which was picked up for a total of 72 seconds, got as far as the letter U. Was this really a sign of life from the universe, or was there a soberingly banal explanation for this? The wow signal laid the foundation for numerous myths, according to which it was something like an alien Arecibo message, especially since it was very narrow band at 10 kHz. As already mentioned, narrow bandwidth could be an indication that a signal was deliberately sent out. Nevertheless, the signal did not stand up to SETI criteria, because it was not repeated, not registered by any other station, and did not contain any information or coding that made sense in any way. Now the objection could be raised that our own Arecibo message didn't meet the first SETI criterion either, because it was also sent out only once. But it very well contained a coded message. However, it was not possible to decipher any content in the wow signal, at least not with the means available to us. Only much later, this mystery was apparently solved. It has been published that the radio emission most likely came from a comet, named 266 Christensen, discovered in 2006. This short-period comet, which comes close to the Sun every 6.5 years, was pretty much in the exact spot where the signal came from, on August 15, 1977. When the comet reappeared in 2017, it was found to be emitting a signal at 1420 MHz, very similar to the one found in 1977, but not as strong. It was about 5 to 6 times stronger than the background noise, while the wow signal was 30 times stronger. It is now thought that the strength of the original 1977 signal was related to the fact that Comet Christensen was much larger and more active 40 years earlier. Now, let's try to calculate how many intelligent civilizations similar to us probably exist in our galaxy. This attempt at a demography is based on the assumptions that the life forms we are interested in need a constant stellar energy source over billions of years to reach a similar stage of development as we do, and that they are located on planets in orbits around stars. Such a count is thus limited to extraterrestrial civilizations that exist under conditions very similar to ours. In order to estimate the possible number of civilizations in our galaxy, the so-called Drake equation was invented, named after the most important figure in SETI research, Frank Drake, who first tried to detect artificial radio signals coming from extraterrestrial sources. The Drake equation uses 7 variables to estimate the number of detectable civilizations in the galaxy. Basically, it is just a product of probabilities. Much has been written and published about it, but first we must clear up a common misunderstanding. The Drake equation does not calculate the number of all intelligent civilizations in our galaxy, but only the number of civilizations with which we can make contact. In other words, those who are capable of interstellar communication. Thus, the equation defines an intelligent civilization very strictly. It must be able to send and receive radio signals. Amazingly enough, according to the definition of the Drake equation, humans are an intelligent civilization only since a few decades. The value n stands for the number of intelligent civilizations in the galaxy, which we could detect and which are capable of interstellar communication. This is the value we want to determine. Our star is the annual average star formation rate in the galaxy, referring only to sun-like stars. As we learned in the last video, not every star provides conditions suitable for life in its vicinity. However, evolution to intelligent life probably requires billions of years, if it takes place at all. On Earth, the transition from simple unicellular organisms to more complex life forms has taken about as long as the evolution from single-celled eukaryotes to humans. Stars that allowed the evolution of intelligent life should therefore have a lifetime of at least several billion years. Today, it is assumed that in the galaxy every year 1.5 to 3 such stars are newly formed, providing suitable conditions for life. Fp is the fraction of stars with planetary systems. At the time the Drake equation was established, this factor was completely unknown. It was not even known for sure whether other stars have planets at all. Exoplanet research is still young, as we have learned in the previous video. Today, the list of confirmed exoplanets includes more than 5,400 entries, and new ones are added every year. Statistics indicate that planetary systems are the rule, and the value of Fp therefore could be close to 1. Ne is the average number of planets in each planetary system, with permanent circumstellar habitable zones, or CHZ. In other variants of the Drake equation, it is the number of life-friendly planets. In fact, several exoplanets have already been discovered in the CHZ of their planetary systems. Based on observations with the Kepler Space Telescope, researchers estimate that there may be about 40 billion Earth-like planets in the galaxy in the habitable zone of sun-like stars or red dwarfs. This suggests that the product of Fp and Ne is about 0.4. Fl stands for the fraction of these planets on which life has actually emerged. This parameter addresses the question of how likely it is that life will actually evolve if the planet allows it. This is primarily about microbial life. But we do not have enough information to determine this parameter. The only certainty is that it must be between 0 and 1. We know that not all planets in a CHZ necessarily support life. In our solar system, according to some definitions, Venus and Mars are also on the edge of the habitable zone. But only Earth is really habitable. A planet must also provide an atmosphere, a magnetic field, the right mass, and many more. Nevertheless, many researchers assume that the development of life is inevitable as soon as it is physically and chemically possible. According to this, Fl is equal to 1. Fi reduces the equation to the fraction of these inhabited planets, on which intelligent life has evolved. We do not know how likely intelligent life is to evolve. Does intelligence always arise, if only life has enough time? Or is it something special? Earth has spawned about 50 billion species during its existence, but only one of them has brought forth higher intelligence, which has evolved in cultural and technological evolution. Thus, the transition from complex to technological life forms could be a major challenge. However, statistics suggest that it is likely that Fi is significantly smaller than 1. The next term, Fc, breaks down the equation to the fraction of these planets on which intelligent life has been able to evolve into advanced civilizations, and that these civilizations engage in interstellar communication. Here, the Drake equation becomes even more hypothetical. We know nothing about how, when, or by what means extraterrestrial civilizations evolve. The underlying assumption is that a civilization will inevitably send signals into space at a certain point in its technological evolution. This could be a conscious decision, but it is much more likely that they are just technology signatures, such as radio waves emitted as a side effect of their everyday activities. However, any estimate of Fc is pure speculation. It is plausible to assume that as a result of involuntary radio emissions, the probability is significant and greater than 0. But perhaps it is much more difficult than expected to detect the signals of other civilizations. Most communication on Earth today is encrypted, compressed, and digital. To outsiders, it might sound like random noise. And maybe that is why our efforts have been unsuccessful so far. In the original formulation of the Drake equation, Fc was estimated to be 0.1 to 0.2. Therefore, We can assume 0.1 as the lower limit here. The last term of the Drake equation, L, is the lifetime of a civilization, or at least the time period during which a civilization is sending out radio signals into space. A civilization, which does not exist anymore, is of course not available for contact. In addition, stars and planets also have a limited lifespan, and natural disasters could also limit the existence of a civilization. Asteroid impacts, neighboring supernovae, gamma-ray bursts, or increased stellar activity have the potential to destroy all life on a planet. Technological civilizations may be able to protect themselves to some extent from such events, but Earth history shows that mass extinctions are not uncommon. All of this would drastically reduce our opportunities to make contact. With an optimistic estimate for the lifespan of a civilization, it is quite conceivable that a technologically advanced civilization could exist for several thousand, or even millions of years. Should they not be able to leave their planetary system, in order to colonize neighboring planets, the limited lifespan of their central star will finally put an end to them. If, however, they succeed in leaving their own star, there would be practically no limits to their survival. It is also conceivable that characteristics necessary to make any species the dominant life form of a planet would be detrimental to its long-term survival. The pessimistic conjecture, therefore, is that advanced civilizations tend to self-destruction. If not by wars, then by destroying their own environments. Such a civilization may not be able to control the negative implications of its own technological development. Thus, we can hardly give a reliable value for the factor L either. Most variants of the Drake equation calculate with more or less 1,000 years up to 1 million years. Thus, the product of all these parameters is supposed to give an estimate for n, the number of intelligent civilizations in our galaxy that could make contact with us. Since the parameters are largely unknown, the value of n varies considerably depending on whether we are optimistic or pessimistic about the many unknown variables. In an optimistic scenario, we assume that every year 3 stars are formed in the galaxy that could produce planets with suitable conditions for life. The emergence of intelligent life is virtually inevitable, and half of all civilizations send out detectable signals. High civilizations have an average lifespan of 1 million years. In this scenario, about 600,000 contactable civilizations could exist in our galaxy. In a more pessimistic scenario, we assume that only 1.5 stars with life-friendly conditions are formed per year. However, the emergence of intelligent life takes a very long time and happens only in 1 out of 100 cases. Only 10% of technological civilizations transmit detectable signals, and the average lifetime of a civilization is only 1,000 years. According to this scenario, 0.6, that is, not even a single communicating technological civilization would exist within the galaxy. We know that there is at least one, but statistically the result simply means that intelligent life is extremely rare and that in another galaxy there might be no civilization at all. However, the fewer civilizations are assumed, the greater are the average distances between them, which in turn makes communication by radio signals difficult or even impossible. In the worst scenario, n equals 1, which would mean that we are alone. So, the Drake equation does not provide a definite numerical value for the probable number of extraterrestrial civilizations in the galaxy. Rather, it shows the difficulties and uncertainties that still need to be cleared up before any serious demography can be done. Scientists argue why we haven't had contact with our cosmic neighbors for a long time. Theories range from civilizations that have never left their worlds for some reason, to aliens that simply have no interest in contact at all. The Italian physicist Enrico Fermi assumed in 1950 that a technically highly developed civilization, which already operates interstellar space travel for millions of years, should have actually already colonized large parts of the galaxy, and according to the probability this should have already happened. In short, Fermi stated a logical contradiction between the lack of evidence for extraterrestrial life and the high probability of its existence. Today, this is called the Fermi paradox. Even if the possibility for interstellar communication exists, the question arises whether a civilization has any interest at all in using this technology. Perhaps all civilizations in our neighborhood have agreed to avoid contact. This speculation is sometimes called the zoo hypothesis. Maybe extraterrestrial civilizations have already made contact attempts and we have ignored them or not noticed them. Maybe they do not exist or no longer exist. Perhaps all civilizations have long since died out. Considering how small the total duration of human existence is on a cosmological scale, maybe it is the fate of all civilizations to fade away after a vanishingly short time in astronomical terms. If we look at our very own civilization and its development over the last 100 years, this is not particularly far-fetched. Overpopulation, war, ecological destruction, natural disasters, depletion of resources, and loss of livelihoods. Watching the news, it is not unlikely to feel that mankind will not have too long and bright a future. Since the beginning of the Neolithic Revolution, human activities have drastically influenced and changed our planet. Today, we feel the implications more than ever. Some authors' point of view is that the rapidly growing human race is infesting and harming Earth like a disease. Therefore, according to some authors, intelligence and the resulting cultural and technological evolution was a misdevelopment. In the opinion of those who represent a misanthropic attitude, humans should never have gone so far. Accordingly, any civilization, which irreversibly exploits and destroys its planet, would be doomed, since they would inevitably saw off the branch they're sitting on. Well, let's leave aside this very pessimistic view. On the other hand, some scientists believe there could have been millions of intelligent civilizations in our home galaxy. However, even if such a civilization could last for an average of 1 million years, most of them should have died out already. But there would still remain a few thousands, which could take up contact to us. But why haven't they done already long ago? If there were really intelligent civilizations in the galaxy, they might have had not only thousands of years for their technological development like us humans, but hundreds of thousands, or even millions of years. Let us exclude the previously mentioned assumption that a civilization cannot exist for a long time, as they may annihilate themselves and their planet sooner or later. If this is not necessarily true, they would probably be so far ahead of us that it would be easy for them to track us down in space and to establish contact with us. Such an advanced civilization, however, should have managed to overcome all the problems that make our own future seem so uncertain. In spite of their technological development, they would have to have learned to take care of their planet. Or they would be forced to leave and colonize space. Perhaps technological civilizations are countless, but for some reason their lifespan was too short to advance their development sufficiently. This is not an unlikely fate for humanity either, as we are still capable of blowing ourselves up multiple times due to our nuclear arsenals. Other scientists again assume that the aliens would probably have no interest in a contact at all, be it because their own world is sufficient for them and they see no reason to expand and explore, or because they consider mankind not yet ready for such an exchange. That is the so-called embargo hypothesis. Maybe they have had us on their screen for a long time, but we haven't been able to notice this yet. Civilizations that engage in interstellar space travel will probably be able to cloak themselves suitably. In fact, some researchers have already investigated for possible alien watch posts at the so-called Lagrange points or libration points. The Lagrange points are equilibrium points for low-mass objects under the gravitational influence of two massive bodies orbiting them. The low-mass object remains almost at rest at this point. For example, the James Webb Telescope was placed and operates at the L2 Lagrange point of Earth and Sun, about 1.5 million kilometers away from Earth. In any two-body system there are 5 Lagrange points, so plenty of choice. An alien cosmic scout, such as a probe, could be placed on one of them with little effort. So far, however, no one has found anything. And if the probe is cloaked, we never will. For some scientists, the most conclusive explanation of why we have not yet seen or heard from our cosmic neighbors, on the other hand, is quite simple. They do not exist. According to this, we are alone in the galaxy. This is also an option, but since this statement cannot be proven either, we are left only with the possibility of disproving it by proving the opposite. According to the current cosmological model, the universe consists mostly of dark energy and dark matter, one being more mysterious to us than the other. Only about 4% of the universe is made up of visible matter. It could be logical to assume that, if we suspect dark energy and dark matter at least to some extent, a more highly developed intelligence most likely already understands them very well. Perhaps they could use these forms of energy and matter, which are still virtually incomprehensible to us, for technologies completely unknown to us, for communication or for propulsion. And then, of course, with our primitive telescopes, we could wait a long time for a message. And if they exist, and if one day we manage to contact them, what might be the possible outcomes of a first contact? If we are not alone in the universe, and if our search leads to a successful result, an immediate consequence would be a lesson in humility. In the long run, after making contact, mankind would hopefully change for the better. We would arrive at a new view of our existence, our origin, and our future. A more pessimistic implication of contact could be the invasion and exploitation of Earth and its resources, just as H.G. Wells described it in War of the Worlds. Presumably, the vast distances preserve us from such a disaster. Interstellar space travel is likely to be as great a technical challenge for most extraterrestrial civilizations as it is for us. But perhaps they would have to leave their planet, if the greatest need forced them to do so. Such an alien race would presumably have nothing to lose. They could, perhaps out of a non-existent or entirely different ethical sense, not bat an eyelash to conquer us. A more subtle danger could be subversion. Under the guise of educational, technological, or scientific support, they could get us to produce the means that would allow them to take over our planet. There is also the risk that we may suffer culture shock from mere contact with a far superior society. Whatever the intentions of an intelligent alien race toward us, our own civilization will not be the same after contact. In particular, we may be in danger of losing our identity, if they are at a higher technological level. Similar to many indigenous cultures that have repeatedly come into contact with modern civilization in the past of human history, and ultimately disappeared. A few years ago, Stephen Hawking, one of the greatest physicists of the 20th century, warned of these dangers posed by possible contact with a superior extraterrestrial race. He said,
"One day we might receive a signal, but we should be wary of answering back. Meeting an advanced civilization could be like the Native Americans encountering Columbus. That didn't turn out so well."
Anyway, if you believe the polls, public opinion is quite divided on whether possible aliens are friendly or hostile to us. What do you think about it? Please write it in the comments. I hope you enjoyed this video. In the next and last part of our series, we look at the phenomenon of UFOs and explore the thrilling question of whether or not aliens have been visiting our Earth for a long time. As always, we would be glad for a subscription and a like. See you next time on our channel.